Okay, good afternoon, everyone. I'll start class with any questions that you might have. Anybody have any issues with homework or need clarification on anything? We're all happy? Okay. All right, so the main ideas from last class were that if we start with a function, f of x, we have this thing that we can do called taking the derivative of it. And what it generates is a brand new function, which we represent with this little f prime of x. So that means that there's a graph for this function, and there's another graph, something different, which would be the graph of the derivative. And the way we take the derivative, in order for us to do this, what we have to do is calculate the limit as h goes to 0 of f of x plus h minus f of x over h. And calculating that limit is a pain in the butt, right? I mean, it can be complicated. The algebra can be difficult. Okay, and so what we're going to be doing today is we're going to be learning that there is a shortcut to taking the derivative. There's another way that we can actually get to our answer. There's a shorter way to do it where we do not have to use the limit. All right, and these are formulas that we're going to be now provided that will allow us to do it, and it'll be nice. Okay. Now, also last class, we talked about higher order derivatives, meaning that if you have a function and you take its derivative, you get this derivative function, and you can do it again, and you can do it again, and you can do it again, and then you have these higher order derivatives. And we said at the very end of class that if this is a position function, then if you take the derivative will be the velocity. If you take the derivative of the velocity, you will get the acceleration. Now, we didn't talk about what happens if you take derivative of acceleration, but in our physical world, these are the only three that really matter, okay, that we deal with the most: position, velocity, acceleration. So even though you could continue taking derivatives, they start to lose physical meaning that we can benefit from. So the first two derivatives, velocity and acceleration, are important. All right, y'all ready? We're going to get into the formulas now. So like I just said, we now establish some shortcut formulas which will allow us to compute derivatives without having to use the limit. This will make our lives drastically easier. Okay, so you're going to be so happy about this. And then you're going to realize that, okay, well, these formulas are great, but now you're going to have more complicated functions to find the derivative of. So as they become more complicated, even the formulas become challenging to use. And if you ever had to go back to the limit, it would just be a complete disaster. So it's kind of like one of those, that common saying, be careful what you wish for, right? Because we're hoping we can get a shortcut here, and we get it, and then we say, oh crap, now things get harder. So let's get through the formulas. There are, at least for this first section, 3, 4, 5, 6, 7, 11 formulas here, okay? Now, I'm going to try and prove some of these formulas. Some of them I'm going to do, some of them I'm not, because it'll just be too hard. It'll take up too much time, all right? So let's look at this first one. The first formula says that if you ever want to know the derivative of a constant, the answer is 0. Now, I can do this proof without really doing anything more than just graphing and visually illustrating this. So if you have a constant function, that means your function is always going to be the same value. Then it would be like y equals, let's say, 4. Okay, so this is a constant function, this red line. And if we want to talk about its derivative, then you go to any point, doesn't matter what point you pick, go up to the function, and then figure out the slope of the tangent line, Well, it's going to be parallel to the actual line itself, and that means that the slope has to be 0. And that would occur at any point I go to. My derivative would be flat, which means that if you graph the derivative, then all of the outputs of the derivative will always be 0, no matter where you are. And that means your derivative function is just the 0 function. And it does not matter where this horizontal line is. If I move it down, like, if I do another one, let's say y equals -1, here, this would have the same property. Does that make sense visually? But the derivative of a constant is 0. Okay, good. So one specific example of this, okay, so a way that, just so you can be comfortable with the notation, if I say take the derivative take the derivative of 4, you would say the answer is 0. That's just, I want you to see the notation. Take the derivative, this means the derivative, this is Leibniz notation. Take the derivative of the function 4 and you should get 0. Another notation you might see is this. Take 4 and then put a little prime mark on it. That means, hey, take the derivative of 4, and that would give you 0. Another way you might write it is I say, hey, let f of x be equal to 4. Well, then f prime of x is 0, all right? So these are all just different ways that you could see this property in action, just different notations. Questions there? Pretty straightforward? Okay, let's move on to the next one. The next formula is that the derivative of x is 1. So let's look at that visually. If I take the function y equals x, that's this diagonal line. And that diagonal line actually has a name. This function here, f of x equals x, is called the identity function. It's called the identity because whatever you plug in is identical to what comes out. So if you plug 2 in, it spits 2 out. If you plug 4 in, it spits 4 out, right? That's why it's called the identity. Now, what's important to us is to talk about the slope of the tangent line. So notice that if you go to any point, x, go up to the function, and then talk about the slope of the tangent line, the slope of the tangent line will be equal to the slope of the line itself, because it's just that perfect diagonal line. And what is the slope of this line? What is the slope of the function x? 1, right? You can tell because there's a 1 in front of that x. So it looks like y equals mx plus b. So if the number in front of the x is a 1, then the slope is 1. Therefore, again, visually, I can show you that the derivative of x by itself is 1. So let's take a look at some notation for that. Try something a little different here. So different ways you could see that, of course, would be this notation. But then another way you could do it is you could write, you could just write x with a little prime mark on it like that. And that's not a 1, that's a little apostrophe. The derivative of x would be 1. That's just another way you could see it. You could also put a parenthesis around the x, do the prime mark, that would be 1. Always, right? It's always 1. Now, the next property is very difficult to convince you of visually. Okay, so let's look at the property. This is a super important property. All right, I'm going to put stars next to this in a minute. This is what's referred to as the power rule. And it is critical for us moving on. Look at what this property is saying. It's saying that if you have x raised to a power, okay, any power, so it's using the variable here n, So for example, if I want to take derivative of x cubed, let's say, right? Then according to this formula, the answer will be whatever the power was, you have that out front. So for us, the power is 3, so I'm going to put 3 here. And then I'm going to have x raised to that power that I started with, take 1 away. So I'm going to do x raised to the 3 and take away 1. And this gives me 3x squared. So essentially the power comes out in front, right? The power comes out in front. The 3 comes out in front. And then it's just x to 1 less than 3, which is 2. And we're done. That's what the formula says. If you go back to last class, let me see if I can find the problem we did. It's early. Yeah, remember this one? Okay, you know what? Hold on. Here we go. This problem right here, I said, find the slope of the tangent line to y equals x cubed at, and I gave you 10 different points. I said, wait a minute, this is way too hard. So instead, we're going to find the slope of the tangent line at x equals a and do it generally. And when we did that, look what our answer was. 3a squared, right? So if we replace the a with x, this just becomes 3x squared. But you see all the work we had to do, right? We do all that work to get to 3a squared. Now, today, I'm telling you, you don't have to do all that work. All you have to do is the power rule. Very nice. Let's do another one, just as an example. If I ask you for the derivative of, let's say, x to the 8th power. Let's see, Matthew Diaz, you here? I see you there. So what do you think, Matthew? Use the power rule. What would the derivative of this be?
It'd be 8x to the 7th power.
Done. Wasn't that easy? Wasn't that nice? Good. All right. Matthew, let's go with you again. That seemed too easy for you. Okay, what's the derivative of the square root of x, Matthew? So first things first, Matthew, that is not written as x to a power right now, is it?
Yeah.
But can you turn it into x to a power?
Yes.
Okay, what is the power? If you have x to square root of x, that's really x to what power, Matthew?
It's to the 1/2.
1/2. Okay, so in case we've forgotten, I think I talked about this last time. If you have x and nth root of x raised to the m, this is always x to the m divided by n. Okay, that's the big formula that we need. So you can always convert from what's called radical notation to rational exponents by using this formula. So what Matthew's noticing here is that even though it's not written, there's a 2 out here and there's a 1 there. Okay, so there's a 2 here and a 1 here, and just using this formula. Okay, now that we have that, Matthew, let's go ahead and do the derivative. So n, this is the n, the half is the n, right? So Matthew, what are we going to get?
It's going to be 1/2 x to the power of -1/2.
Okay, good. So how did you get -1/2? You took the 1/2 that was there and you subtracted 1, right?
Yes, sir.
Took the 1/2 and subtracted 1. And that, look, everyone, that's just subtracting fractions. So I'm going to do it on the side here, but you have to get good at this. 1/2 take away 1 is the same as 1/2. Get a common denominator, 2/2. That's 1 minus 2/2, and that gives you -1/2. If I were you, I would just start, like, if you want to practice this, if you're not good at this, just start taking just random fractions and just subtracting 1 from them. And you'll start to catch on to the way it works. You want to be quick with it. So then that becomes 1/2 x to the -1/2. Good, Matthew, thank you.
Thank you.
Caitlin, are you there?
Yes.
Okay, Caitlin, do you remember in some other class that you took that if you had a negative exponent, you could do something with it? Like if you had x to the -2, that you could rewrite that by doing what? Does that sound familiar?
By multiplying?
Like this, if I wrote x to the -2, that really meant you could drop the x down to the denominator. You remember ever seeing that? That this becomes 1/x². Like if you don't want a negative exponent, you can drop it. You remember that, Caitlin?
No, yes, I do.
Okay. So Caitlin, with that property, could we take this and rewrite it as 1/2 times 1/x to the half? Would that make sense to you?
Yes.
Okay. Now, Caitlin, what if I were to ask you to go back from rational exponents back to radicals? How could we rewrite x to the 1/2? We could write it as what?
The square root.
Yeah, the square root of x, right? And that, if I multiply these two fractions straight across, I just get 1/2 root x. Everyone follow that? So at the end of the day, here's what we're saying. We are saying that if you take the square root of x and you take its derivative, you will get what Matthew said, 1/2 x to the -1/2, which is correct. But another way you could write that is what I was just discussing with Caitlin, which is this. I strongly advise you to memorize that, because this is, we take the derivative of square root of x a lot here and in Cal 2. So please remember that the derivative of the square root of x, the way I like to think about it, is 1/2 root x. Now, I always keep in mind that this is true, but I just memorize this. The derivative of square root of x is 1/2 square root of x. Done, move on. So very important one. Okay, let's try something else. Let's try another one. We'll get another volunteer that I'm going to appoint. So in other words, not a volunteer. I want the derivative of 1/³ root of x. And let's go with, I'm trying to find people here I haven't called on in a while. Looks like I got, oh wait, hold on. Christian, is Christian here?
Yeah, I'm here.
Okay, so Christian, in order to do this problem, Christian, we need to be able to rewrite that as x to a power, right? Now, I want everyone to be extremely careful here, extremely careful. Do y'all agree that the numerator is a constant? Y'all see the numerator as a constant? And then the denominator, you could look at the denominator as being x to a power. You agree? So like you could look at this as being 1/x to the 1/3. Y'all agree with that? And we're asked to find the derivative. Didn't I tell you earlier that the derivative of a constant was 0? I told you that earlier. And the top is the constant. And the bottom is a power of x, and I've just told you the formula for the derivative of the power right here. So you might be tempted to just take the derivative on top and get 0, and take the derivative on the bottom and get 1/3 x to the -2/3. That I did by pulling the power out and subtracting 1 from the power. You might be tempted to do that. It's completely wrong. And here's the reason why. I have not told you that if you have a fraction and you want to take the derivative, that you can take the derivative on the top and bottom separately. I have not told you you can do that. I have only told you that if you have a constant, by itself, the derivative is 0. I've told you that if you have x by itself, the derivative is 1. And I've told you if you have x to a power, the derivative is this power rule. I have not said anything about a fraction, have I? I've not, okay? It's going to turn out that taking the derivatives of fractions is going to suck, okay? It's going to suck, all right? But this is completely wrong. So, Christian, if we cannot look at this as a fraction and do top and bottom, is there any way you can make that look like just x to a power?
we could like sort of try the process in reverse that we did on the previous one.
Okay, so you're saying like take it and yes, do write it as x to the 1/3 on the bottom, right? But then what? This is the critical step. With Caitlin, what we did was we had something, where was it? Right here. We had this and we dropped it down to the bottom, didn't we?
Yeah.
I think what you were suggesting, Christian, was to go the backwards and bring it back up. So if you were to take this expression and you were to bring that x to the 1/3 back up, then what would it be?
Would it be x to the third because you flip it?
Don't flip it,
Or
just
no?
change the sign. That's all.
Oh, you
not
just changed
flip.
sign. Okay.
So it becomes -1/3. Right? Because if you have there was a property in college algebra that said if you had x to the -n, you could rewrite that as 1/x to the +n. So negative exponents get dropped down. If you want to bring an exponent up, it has to become negative.
Okay.
All right, is that clear to everybody? I have not done any derivative yet. All I have done was taken the original problem, 1/³ of x. First, I rewrote the cube root as x to the 1/3. I've not done any derivatives. Then Christian said, let's push this back up to the top. Now I have x to the n, right? This is now the n, and I can use the formula from, well, the power rule. I can use this power rule. You want to keep going, Christian?
Sure. So it'd be -1/3 x.
Okay, so we're using the power rule now, so I don't need to have this notation anymore. It's just -1/3. That power comes down, x to the, now let's just write it down, Christian. Let's write it down first, then we'll go calculate it. It should be
-1/3 - 1.
-1. So I need to do -1/3 -1. If I do that over here,
It'd be -4/3.
-4/3. So I just change the 1 into a 3/3, and then do -1 - 3 over the common denominator, and that gives me -4/3. So this should be -1/3 x to the -4/3, and we're done. That's an answer, okay? That's an answer. Now, you can keep messing with this if you want to. I told you on the square root, I showed you how to work through it. The reason I showed you on the square root one, how to continue and get a nice clean answer, is because it comes up so often. The one we're working on right now doesn't come up as often. So that's why I put stars next to this one and everything. This one, this boxed answer would be fine. But if we wanted to do more with it, if we did, here's the algebra. We could take the -1/3, leave it there. I can rewrite the second factor as 1/x to the +4/3. That's just taking that and dropping it down. And then I could use the property of converting that over to a radical. This would mean the cube root of x to the 4th. And then I could put it all into a fraction. Like that. So like I said, what's in yellow here would be an acceptable answer. But if you saw this, like in the back of the book is the answer, then don't be surprised. Like all they've done is just cleaned it up with a little bit of algebra. Questions? Okay. So this is pretty powerful, this rule. It's very powerful. Let's see, did we do another one? Another one. Oh, look at this one right here. Ah, I did the +3. Can't do that one, sorry. Yeah, okay. All right, now, I'm debating whether or not I'm going to prove this one to you. I've given you the formula. I've shown you how it works. Do we want to see the proof? Let me take a poll of the class. Do you actually want to see where the formula comes from, yes or no? And I'm just going to go on a simple majority. Whatever people want to see, I don't mind. Not going to hurt my feelings. Okay, we have a strong majority. So, oh, oops, cancel. So we had out of, I didn't let everyone vote, but 14-1 already. So I'm going to show you where it comes from. Okay. All right. So here's what we're trying to do. Oops. I want to prove that if you take the function f of x equals x to any power, that when you take the derivative of that function, you get n x to the n minus 1. That's what I want to prove, right? I want to prove that that's true for any n. Now, to prove this, I actually have to establish one thing first, okay? And this is something you may or may not have seen in your life. If you've never seen it, it's kind of cool. And it's going to seem like what I'm doing right now, you're going to be like, what the hell? Why are you doing this? This has nothing to do with what we're doing. Just trust me, we're going to need it, okay? So if I were to take an expression, like let's say I take x plus y, and I raise it to the 0 power, what do you get if you raise something to the 0? Nope. You get 1, okay? You get 1. I'm seeing people saying 1, so we get 1. So I'm going to write it like this. Now, I'm leaving a big gap in here for a reason. X plus y to the first power is 1. What would x plus y to the 0 power is 1. What if I do x plus y to the first power? Well, anything to the first power is itself. So this would become x plus y. I'm writing it this way for a reason, okay? Now, what about x plus y squared? Well, that you would have to do x plus y times x plus y, and you'd have to FOIL. And if you did that FOIL, you would get x squared plus 2xy plus y squared. Do y'all trust me that that's true? Okay. What if we did cubed? Well, then you would have to do 3 of them multiplied together, which I would hope everyone in this class could do that. If I gave you enough time, you could start foiling it all out and expanding, and you could get an answer. I'm not going to go through all the work, but I hope you trust me that the answer would be x cubed plus 3x squared y plus xy squared plus y cubed. You've probably seen x plus y cubed or something like it. At some point in your life, you probably had to cube a binomial like that. But what about the 4th power? Well, the 4th power, that's a little bit harder, right? You have to take 4 of them and multiply them together. So let me see, I'm going to look it up. No, I'm not going to look it up. I don't need to look it up because there's a pattern here. Let's see, this, and this. Okay. That's what happens if you take x plus y to the 4th power. You get that. Do you believe me? Okay. You can check it yourself. We're not going to check it right now, but that's what you get. All right. Let's see if I'm going to write the next one down, and then maybe after I write the next one down, you'll start to see the pattern. X cubed y squared, x squared y cubed, x y to the 4th plus y to the 5th. So if you take x plus y, 5 times multiplied together, you get this. All right. What's the pattern? let's talk about x's first, okay? Let's talk about x's for every single one of these rows. The x on the far left, the power on that x matches the power we have here, right? Cube, right? Those powers match. And if you go to one of these rows and start moving from left to right, what happens to the powers on the x's as you move from left to right? X cubed, x squared, x, and gone.
They're
What's happening to them?
decreasing. They're decreasing.
They're decreasing, right? X to the fourth, x cubed, x squared, x, and then gone. X to the fifth, x to the fourth, x to the third, x squared, x, gone, right? So as you move from left to right, the powers on the x's go down. How about the powers on the y as you move from left to right?
They increase.
They increase.
That's right. They start at nothing, right? There's no y's over here. And then when you move over to the first step, now you'll have y. The next step over, y squared, right? And that happens for each one of these rows until you get to the very end. And at the very end, the power here matches the 5, right? You stop when you get to the powers, the power on y to match, and the x is gone. Okay, so the pattern of this is that if I take, let's just say I go down here and I take x plus y to the nth power, okay, to the nth power, what would my first term be?
Be x to the n.
It would have to be x to the nth power, because this power has to match that power. What would be the last term?
Y to the end.
Y to
the end.
Okay, y to the n. Now, let's see if we can't figure out what the next term would be. Okay, so for the next term, let's talk about the x's. What power on x will I have here on this one? If this one
N
was
minus
n,
1.
what would this be?
N.
N minus 1.
1 less than n, right? So
Yeah.
like this is a 5 on the x, this one's a 4. If this one's a 4, this is a 3. If this is a 3, this is a 2. So if this is an n, this is 1 less than n. So the way I write that is x to the n minus 1. That would be this next term, wouldn't it? But I also should have a y next to that, because like we said, the pattern is that as you move from left to right, the powers on x go down while the powers on y come up. Now, I'm missing a coefficient in here. Okay, I'm missing the number. So can y'all see there's a pattern in these numbers too?
Would be 6.
4, 5. What is it?
6.
Is it 2,
Or-
3?
The
I
N.
know it looks like 6. I know it looks like 6 because you're thinking the next one would be a 6. Okay, yes, I agree with you. The next in this pattern would be a 6. But I'm saying if this is an n, what would
Would be
this
n.
It would be N.
Would be n? Because again, this number here actually matches the power on every one of these. The 4 matches the 4. This 3 matches the 3, right? So that means that this n, right? This n that matches here should also match here. So that should be an n. Go with me? Plus, now my next one, I'm going to have an x, now n minus 2 and y squared. So that's the next term, because the power in x got decreased again. So I had to take another 1 away, and my power on y came up. And then there's a number in front here, isn't there? Now that is not as easy to figure out a pattern on, because this is 3, then it goes 6, then it goes 10. So I'm just going to put a question mark here, okay, and not worry about it right now. The next one I would have would be some number in front, which I don't know. And then it would be x to the n minus 3 and then y cubed. So again, the power comes down on the x and the power on y goes up. And then this continues to happen, dot, 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 until all the powers on x come down and all the powers on y come up, and you finish off at the very end with y to the n. You okay with that? Okay. Now, that's all we're going to need, but I want to point something out here. On this picture that I have drawn here, I want you to look at just the coefficients, just the numbers. Okay, so I'm going to circle them, or I'm going to highlight them. The number 1, and then in front of that x, there's a 1. In front of this y, there's a 1. Then we have a 1 here. Then we have a 2. Then we have a 1, right? Let me write these in. We have a 1, 3, 3, 1. We have a 1, 4, 6, 4, 1. We have a 1, 5, 10, 10, 5, 1. And so these are just the, ooh, that didn't work. There, 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 there. One more. There, 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 there. Look at just the numbers. I'm going to write those down here. Just the numbers in the same format. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. Okay, so this is known as Pascal's triangle. Pascal was a mathematician. I'm not sure why Pascal gets credit for this, because the Chinese had discovered it many, 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 many years before him, but Pascal gets credit for it, so, or at least his name's on it. So the way this works is that on the triangle, every number on the end is a 1.
Mm.
And then the next number is just, do y'all see the pattern?
Yeah. Oh.
Yeah, no, what do you see? What should the next number be?
It would be 6.
6, and that's the 5 and the 1 added together. The next number would be these two added together, which
15.
is 15.
And
Then
then
these
20,
two added together, which is
15,
20.
6.
Then 15, then 6, and then 1. And if you go and look at any of these numbers, that's where they came from. 1 and 4, 4 and 6, 6 and 4, 4 and 1. 3 and 1 gave you the 4, 3 and 3 gave me 6, 3 and 1 gave me 4, 1 and 2 gave me 3, 2 and 1 gave me 3, 1 and 1 gave me 2. So let's see if that, if we could actually use it. I want to go back up here. If I were to ask you for the next one, x plus y to the 6th, we didn't do the 6th one. The way you could do this is just look at your numbers. Okay, you know that the first one's going to be 1 and then x to the 6th. You know it's x to the 6th because the power has to match. Plus, now to get the number, you do 1 and 5 together, that gives you 6. Now use the pattern that x power comes down, y power comes up. What's the next number? 5 and 10, right? 15. Now the power on x comes down, power on y comes up. My next number, 10 and 10.
Be
20.
20.
X cubed, y cubed. Power on x comes down, power on y comes up. Then 15. Where am I? X to the 2nd, y to the 4th. That was these two together. Now I have 6, the 5 and the 1 added. Now I have x and then y to the 5th. And I finish off with the final power y to the 6th. All right. Pretty cool, huh? There's a ton of patterns in Pascal's triangle. There are a bunch of different patterns you can find. We're not going to get into it. All right. Now, let's go back to what I wanted to do. I wanted to prove this, didn't I? That if you have x to the n and you take the derivative, you didn't realize that it was going to take this much work. You probably would have said no if you would have realized it's going to take me 20 minutes, 25 minutes. All right, so here we go. We have to act like nobody has given us a formula, which means we have to go back to the definition of the derivative. So the definition of the derivative is that we need to take the limit as h goes to 0 of f of x plus h minus f of x all divided by h. That is the pure definition of the derivative. Now for us, the function we're dealing with is x to the n, right? That's the function that's been given to us. So that means I need to take the limit as h goes to 0 of f of x plus h, which means you plug x plus h into this function, which means we replace this x with x plus h, which would give me x plus h to the nth power. That's what this top left is. F of x plus h into that function would be x plus h to the n. Then we subtract from that f of x, but f of x is just x to the n power, and all of that over h. You following me? Now, I need to figure out what x plus h to the n is. Well, like generally that would be hard to do, wouldn't it? Like what's x plus h to the n? Well, you're not telling me what n is. So I'm not gonna be able to do it. But didn't we just do that? We did, didn't we? We said if you have x plus y to the n, here's what it turns into. But we have x plus h to the n. So I'm just gonna rewrite this, and I'm gonna replace all my y's with h's. I'm gonna slap that down here so you can see it. So using what we already established, this should be equal to limit, you know what, I'm gonna do it here. Limit h goes to 0. This in green becomes x to the n plus n x to the n minus 1 times what? What do we have instead of y?
H.
So times h plus some number that I never figured out, then x to the n minus 2 times h squared. So replacing that with h plus some number, I don't care what it is, x to the n minus 3 h cubed. That's this, plus a bunch of crap that I don't even know, and then h to the n at the end. Anybody have a question on that? That's just the green. That's just the green part. What do I still have to subtract from that? Minus x to the n, right? Divide all of that by h. Now, when you look at that, you're like, what the hell? You know, this looks crazy. How am I ever going to figure this out? But great things happen. Look, the x to the n's canceled. The one in the front and the one in the back are gone, aren't they? Now, what can you tell me about every single term that is left? Something important about every term that's left here.
They all had h. Yeah.
They all have at least one h, don't they? Every single one of them has at least one h. So I'm now going to factor an h out of the top. So if I factor an h from this one, right, I'm going to pull an h out. If I factor an h out of this one, all I'm left with is n x to the n minus 1 plus some number I don't know, x to the n minus 2, and then what's the power on the h that's left here?
1h.
This 1h, right? It's just going to be an h. There we go. And then I have plus, now I don't know this number, and this is going to be x to the n minus 3. And I pulled an h from here, so I should have an h squared here. Plus dot, 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 till I get to the end. And I have taken one h out here, so the power should be 1 less than it was to start. If the power was n, now it's n minus 1. All of this divided by h. And these h's cancel. And we are there, okay? This is the beautiful part. Let h go to 0 now. Look at what pieces of this expression have h in them. Well, there's an h here, right? That has an h. So if I let that h go to 0, it's going to kill everything in there, and this whole thing's going to go to 0, isn't it? This has an h in it. In fact, it has h squared, so that's also going to go to 0. The one at the very end has an h in it, so it's going to go to 0. And what can you tell me about all the ones in here?
They'll have an H.
right? They all have H's. Every one of them has an H. So they're all going to go to 0. So what's the only thing left after all this stuff goes away?
And
The
X
first.
Right there.
minus 1.
And that's the answer. N x to the n minus 1. There you go. We have proven the power rule using the limit. And that took a while, okay? It took a while. That's why some of these I'm not going to prove because they just take too long. And if you're interested in them, I'm happy to do them. Just you have to come to my office hours for it. It's just not enough time, all right? What I guess I'm trying to tell you is that I don't want you to think that all of these formulas just kind of fell out of the sky, right? Like we had to come up with them. Coming up with them is hard, but we are going to take them on faith. But just realize there is a proof for each one of them, for every formula I give you. All right, back to the formulas. The almighty power rule. Okay, the next one is called the constant multiple rule. And this is not a really complicated rule. Let me show you how it works. All this constant multiple rule says is that if you have a constant attached to a function through multiplication, that what you can do if you want to know the derivative is you can just bring the constant with you and take the derivative of the function that you see. Let me give you an example. Let's say I wanted you to take the derivative of 3x to the 4th power. Okay, so this notation means, hey everyone, take the derivative of this. Naja, are you here? I see Naja. Let's see.
Yes, sir.
Okay, how are you doing?
I'm doing good.
Okay, so Naja, you see here that we have a constant multiplied by some function of x. You see
Mhm.
that? This rule says that this derivative should be equal to just the constant, okay, right? Just the constant. So what would the constant be for us?
3.
3 times, now, Naja, what's the derivative of that function that we have here?
4x to the 3rd.
Or x to the 3rd. Now you just use the power rule, right, for that? And then you can multiply the 3 and 4 together and just get 12x cubed. So the way I like to think about this, Naja, is that if you ever have a constant times a function and you want to take the derivative, I always like to say the constant just comes for the ride, okay? It comes for the ride. Now, Naja, what if I asked you this? What's the derivative of 3?
0.
0, and that's because it's by itself. It's a constant alone. The constant multiple rule requires that the constant is attached to a function. If the constant is attached to a function, then it comes for the ride. If the constant's by itself, it goes to 0. You want to see something pretty crazy? I'll show you something pretty crazy. Look, this rule right here, let me show you. Do you all agree that I could rewrite 3 as 3 times x to the 0? Do you all agree that that's the exact same thing? The number 3 is the same as 3 times x to the 0 because x to the 0 is 1, isn't it?
Mhm.
Right? So if I ask you to take derivative of this, doing what Naja just said, we can bring the 3 for the ride times, now do the power rule on this. Do the power rule. So what comes out?
0.
0. So you get 0 x to the negative 1 because you subtract 1 from 0. But none of that matters because what's your answer? Well, we
0.
got a 0, right? So the answer is 0. All I'm trying to show you is that if you want to convince yourself that the derivative of 3 is 0, you can still use the constant multiple rule and the power rule to convince yourself it's true. Okay, let me do another one. Good job, Naja. How about this one? How about if I have pi times x to the pi, and I want to know the derivative. Daniela?
Yes,
How's it going,
thank
Daniela?
you. Good, thank you.
Good, good. Okay, so Daniela, do you see that we have a constant? Pi is a constant, right? Pi is just a number, everyone?
Yeah.
Times, this is some function of x.
I can't.
So Daniela,
Okay,
what-
I walk
what
away
happens
for
to the
1 second
constant?
and like I missed so much.
What's that, Jair? Did you have a question?
Oh, so sorry.
No, it's okay. Daniela, so the constant that's attached to the function, what will happen to it when we take the derivative?
It will just come,
Okay,
like, it will be just pi.
this pi. Okay, now this is the tricky part. Times, what's the derivative of x raised to the pi? So what are we gonna do? Go ahead.
So do I have, is that just one or,
We know how to take the derivative of x to the n, right? The derivative of this, the n comes out, and then we subtract 1 from the n and raise x to that power. So
Yeah.
my question is, pi is just a number, isn't it?
Mhm.
Okay, so let's just use the rule. So what comes out front?
pi?
Pi. So you have another pi here, right? And then
Yeah.
x, what power?
Pi minus 1.
Pi minus 1. And that's it. Now we can do one more thing. We can multiply those pi's and become pi squared, x to the pi minus 1. But that's it. That is the answer. Pi squared, x to the pi minus 1. Now pi minus 1, you can't really figure out what that is unless you want to use decimals, right? You could do pi on your calculator, subtract 1, but it's going to be an approximate. So I'm going to leave it just like this. This is the exact form of the answer. Okay, that's the constant multiple rule. Next one, the sum and difference rule. This is a really nice rule. This rule says that let's say you want to take the derivative and you've got some function of x and you're adding or subtracting from it some other function of x. So you have two things together through addition. This rule says that you are allowed to split this up and do the derivative of each one of them separately and then add or subtract the answers together. And this may seem very intuitive and very natural. Let's do an example. Let's say we have 3x to the 4th plus 7x to the 3rd, and I want you to give me the derivative of that. So Alejandro, are you here?
Yes, I'm right here.
Okay, are you following so far?
Yes, sir, I believe so.
Okay, so Alejandro, this is the first time that I've given you something to take the derivative of where you have two terms. In other words, there's an addition or a subtraction between them. Nothing we've done up to this point today has had more than one term. Everything's been just a single term. But now with this rule says if you see addition or subtraction, you are allowed to just take each one of them and do them separately. Do you see this? Do you see the rule in action here? Do you see how I've written that and how this represents that rule, Alejandro?
Yes, sir.
Okay, so now just give me these answers. So,
All right. So for the first one, it's going to be 4x to the 3rd power.
okay, and what happens to the 3 that's in front?
Oh, it's going to multiply. It's going to come right along with it. So it's
Yep.
going to be 3 times 4x to the 3rd power.
Okay, good. Keep going. This one.
Then for the next one, it's going to be, well, the 7 is going to ride along too.
Mhm.
Then it's going to be 3x to the 2nd power.
There we go. Good. Last thing would be just multiply these numbers together. So 12x cubed plus 21x squared. We're done. Now, if you will get to a point in this class where you're no longer writing 3 times 4 and 7 times 3. You just bring the 4 out, hit the 3 and become the 12. Bring the 3 out, hit the 7, become the 21. Okay. You don't need to show this step. I just didn't want to jump from here to here. Good, we're done. Okay, that's a nice rule. The rule just says you're allowed to do it, okay? There's a proof. I could go through the proof. I could show it to you, take us 45 minutes. We're not going to do the proof. But you cannot assume that you can do this. You can never assume in math that something is the way you think it's going to be. You always have to prove it's that way, as you're going to see here in a little bit. Okay, next one is just some things you need to know. So the derivative of sine of x is equal to cosine of x. All right. If you take the sine function and take its derivative, you get the cosine function. We talked about this last class. I think, was it Brian? Did you say that? I think Brian said that in class last time, that when I graphed the sine function, we were looking at its derivative, that it looked like the derivative was the cosine function. Well, it turns out it is. It is exactly the cosine function. I'm going to prove this one. Okay, I think it's worth seeing the proof for this. All right, so I want to prove this. It shouldn't take me 45 minutes. This should take me about 10 maybe. I want to prove that if f of x is sine x, that the derivative of that is cosine x. Okay, I'm going to prove it. So the only thing I can use whenever you do a proof, the only thing you can use is the limit. So this means that I have to show that the limit as h goes to 0 of f of x plus h minus f of x over h. I want to show that that's going to turn out to cosine x. Now the function we're using is sine x, and we are plugging x plus h into that function to get this top corner. So that means it's going to be limit h goes to 0 of sine of x plus h plugged in. That's the blue part. Right, we're just plugging x plus h into that function. There it is. X plus h into sine gives you sine of x plus h. We subtract from that still f of x, but f of x is just the sine function itself. And then divide the whole thing by h. Okay. Right, so there's where we are. Okay, there's where we are. Now, this is the part that's tricky. Is right now, if I let h go to 0, we will get 0 over 0. And there's no real algebra that you can do to make this nicer. Please don't try and do this. Sine of x plus h does not turn into sine of x plus sine of h. That is no, okay? That's not what happens, okay? So what we can do, though, is we can go back to pre-cal. And we can go back to our formulas in pre-cal. There was one right here. This one. Oh. I can use this formula from pre-cal that if you ever have sine of something plus something, it can turn into this. So for us, we have x plus h, not x plus y. So this becomes limit h goes to 0 of sine of x cosine of y, but for us y is h, plus cosine of x sine of h. And that's the blue part. And then minus the sine of x that was there in green still. And then all of this is over h. Any questions there? Okay? No questions? Here we go. We're almost there. Limit h goes to 0. All I'm going to do now is rearrange things algebraically. So I'm going to move this minus sine x right here. And so it becomes sine of x cosine of h minus sine of x. And then I have plus cosine of x sine of h. The whole thing over h. Do y'all follow the algebra right there? Just slide that over. Next thing I'm going to do is I'm going to ask you to remember that if you have a bunch of different terms on top and a single term on the bottom, you can break this into multiple fractions. So I'm going to just split this up into this over h and this over h. Instead of everything over h, it's just each one of those over h. And then do one more thing. Limit h goes to 0. On the numerator here in yellow here, both of those terms have a sign. So I'm pull a sign out, sine x. I'm left with cosine of h minus 1 over h. And then plus cosine of x sine of h all over h. We're done. We're there. Okay. Any questions on that? What I've done so far? I'm gonna let h go to 0 now. So I want to point out first that right there, sine of x doesn't have an h in it. So h has no impact on that. Same with that cosine of x. That does not have an h. The only thing that has h's is this piece and this piece. Do you all recognize sine of h over h? That when you take its limit as h goes to 0, do you remember what that becomes?
Is it
Sine of
1?
h. What is it?
Does it become 1?
1. That's that sine of junk over junk. As long as the junk matches and the junk goes to 0, right? That
Yeah.
goes to 1. So that means this whole thing is just going to go to cosine of x times 1, which is cosine of x. Plus, now this one, this is the other special one that I told you you should know. This one, if you look back on your notes, that limit goes to 0. And so if that goes to 0, this whole thing goes to 0. And 0 plus cosine of x is cosine of x. And that shows that the derivative of sine of x is cosine x, using the definition. Okay. What do you think the derivative, well, you know what, let me do this before I do that. I'm going to graph sine of x, there's sine of x. I'm going to graph its derivative right there. You know what, we don't need this. I'm just going to get to it. Okay, so the derivative of sine of x is cosine x. The derivative of cosine of x is not sine x. It's negative sine x. So that throws a little wrench in things. It's real nice that the derivative of sine of x is cosine x, but when you do derivative cosine, it's not just sine, it's negative sine, so don't forget that. And that's just the derivative of the first two trig functions, right? In pre-cal, you learn all these trig functions, sine and cosine. Here are the derivatives of each of those. And then we can continue. And here are the derivatives of the remaining 4 trig functions that you learned in pre-cal. I'm not going to prove these. And it might take you a minute or a couple of days to memorize these, but just in case, don't worry about copying them, because if you go onto your formula sheets and you get to reference page 5, differentiation rules, that's rules for derivatives, you will see here what we've covered so far on this formula sheet. You will see here that the derivative of a constant is 0. We just talked about that. We have talked about that the derivative of a plus in between two functions, you can split it up into 2. This is the constant multiple rule, that constants come for the ride. This is the rule that says that if you have subtraction between two functions, you can do them separately. And we did the power rule, which is this one. We have not done 5 yet, we have not done 6, and we have not done 7. That's the next section, which we're going to do today. But if you continue scrolling down here, which means I'm going to lose that. Come on, scroll. There we go. If you continue scrolling down, you'll see here trigonometric functions. You'll see their derivatives here. Derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of tangent is secant squared. Memorize the first 3. You need to know those. The next 3, just know where they are. And then maybe if you're going to be a serious Cal 2 student, you'll have those memorized too. All right. So I'm just trying to tell you, there's a reference here for you. Okay, there's a place to reference this stuff. Okay, let's do this. I'm going to give you some problems to work on your own right now, or I'll put you all in groups for it, okay? And let's see what you can do here in the next, I don't know, 10 minutes or so. And then we'll continue to the next section, all right? So first problem I want you to do, for all of these, I want you to find the derivative. So I'm going to give you the function, and you go find the derivative. So first one here, we'll start kind of simple. That's a slight change from the first one.
Excuse me, for number 3, does it right there, is that a 3?
That's a 3. Yeah, I'll make this a little
Okay.
bigger.
Thank you.
Yep. This is cube root, 4th root, cube root again. All right, there you go. Copy those down and put you in breakout rooms. Let's see how far you can get. I'll tell you that every one of these can be done with the rules that we've learned up to this point, okay? So just take your time through them. Breakout rooms, there's going to be somewhere between 3 to 4 people in each room. Please help each other out, at least check your answers with each other. Like, are you getting this? Are you getting that? Okay, everyone, we're gonna take our break now. 10-minute break, but I have the solutions up here. So you want to maybe look through those and make sure you're getting what you're getting. And I'll give you a couple of minutes to do that. So let's say we're coming back here in about 13 minutes. If you have any questions, I can answer questions right now before I take 10 minutes. Does anyone need clarification on any of this? Just let me know. Okay, I don't think everyone had come back, so I'll just repeat myself. We're going to take our break. Timer's here. We're going to take about 12.5-minute break. For the next like 2.5 minutes, I'll answer any questions, but feel free to take a break if you'd like to now. If you need any clarification, just let me know. If you got it all, then good. You're ready for the next step, the next section. Okay. So no questions on these problems. We're okay with that? So I'm going to send you after class, I'm going to send you a review for the exam, which is a week from today. And that review, what I'm going to do is I'm going to send you the review that I used in the spring for my class. So when I send you that review, I'm going to send you that and their exam 2 review, because there's a couple of problems on their exam 2 that's going to be on your exam 1 because summer is condensed. So when I send you these 2 reviews, just make sure that you pay attention to the instructions, because I will tell you which problems to look at and which ones to not worry about. I don't want you to look at both of them and be like, oh my God, I don't know half this stuff. You won't know half of it. So just pay attention when I send that out. I'm going to show you though on the exam 2 review, I'm going to show you a problem. One of my favorite types of problems to put on an exam. So I'm going to take this one here. Let's just take a look at it. I'm not going to work it out. I'm just going to tell you how you would go about it. So for this problem, you have to realize you have 1, 2, 3, 4 terms in the numerator, and you have 1 term in the denominator, which would allow you then to break this into 4 fractions. You could do this over that, then do this over that, then do this over that, and then do this over that. So for example, on the first one, if you take the -4 root x and divide it by the root x, well, let me just write them all down. This is what it turns into. Now what you want to do is rewrite this where you have x to a power. So on the first one, these root x's go away, so you just have -4. That's easy. The second one is the one I want to show you. This right here, you have to simplify this before you can take the derivative. So that becomes x cubed over x to the half, which is x to the 3 minus a half. This is just properties of exponents. I'm not taking a derivative here, just using properties of exponents. And that becomes x to the 5 halves. So your second term here becomes plus the 6 that was there, x to the 5 halves. And then you continue and you get the rest of it. And then you take the derivative on each one. Okay, so just pay attention to that. I had not given you a problem like this. Just be aware that you can split it into multiple pieces because you have 1 term on the denominator. Any questions there on how to approach that? Okay.
Excuse me. I didn't see the answer for whenever you posted number 5. Can you show that real quick, please? Or like go over it?
Oh, I didn't. Yeah, I'm sorry. I thought I had scrolled down all the way. You're right. I didn't. There's the answer for 5.
Thank you.
Okay, we're ready to move on to the next set of rules or shortcuts. All right. So this is the next section in the book 2.4, which is called the product and quotient rules. So here's where things start to get messy. All right. Right now, all you know how to do is take the derivative of a constant by itself, which is 0, the derivative of x to a power, which you use the power rule, and then you know how to do a constant times a function. You just bring the constant for the ride. And then you know how to deal with addition and subtraction. And then you know the derivative of sine, cosine, tangent, cotangent, secant, cosecant, all those. That's where we are. But now it's time to look at something like this. What if we get a function f of x that looks like, how about x squared sine x? So we have multiplication occurring between 2 functions of x. Do y'all see that? We have x squared, times some other function of x sine x. Now, you might think that the derivative of this is a question, is this true? That it's just 2x times cosine x. So can you all see what I did? I just took the derivative of x squared, got 2x. I took derivative of sine x and got cosine x, right? It would be nice if that were the case, but it is not the case, okay? This is not the way it works when it comes to multiplication. We have a rule called the product rule, which tells us how to take derivatives of products. I'm not going to prove the formula. I'm not going to prove the rule again because it would take too much time. But here's what the rule says. Let me bring up the notes. And this is a little nasty to look at when you see it first, but it says that if you want to take the derivative of some function times some other function, okay, so two functions being multiplied, then what you're going to do, okay, this is where things get ugly, is first you're going to take the derivative of the first function f. You're going to take its derivative, and then you're going to multiply it times the g function, which is the second one, but you're not going to take the derivative of the g. So you take derivative of the first one, f, multiply it times g. Then you add to that, now you take the derivative of the g function, and you multiply that times f, but you don't take derivative of f. It's weird. And again, I'm not going to prove to you why this is the way it is, but that's the rule. This is a shorter way of writing it. If you have two functions being multiplied, let me do this on a different page. The product rule says, if I have a function f times a function g, and I want to know what the derivative is, it's the derivative of f times the g plus the derivative of the g times the f. And that is your product rule. So what you have to do to use the product rule is you have to first look at the function that's given to you. You have to realize that you have a product. And then once you have a product, you need to identify which is the first function, what's the second function, what's the f, what's the g, and then go ahead and just execute the formula. So let's take the problem I had up here. I'm going to write it a little different. I'm going to call it y equals x squared sine x. That was a problem we had to start here, right? So I realized first that I have a product. So I'm going to note that I have a product here. And I like to put a little dotted line between so I can see the product. And then I like to call the first one f and the second one g, just like that. And so if we want to know the derivative of this, it's going to be the derivative of the f function first, right? So f is the x squared, so I'm going to be taking the derivative of this. I have not done it yet, but I'm going to take derivative of that and then multiply that times the g, which is sine x. Then add to that, now I take the g and I take its derivative, and then I multiply that times the f, which is the x squared. So I hope that you can see the way I've written this. This is f prime times this is g plus this is g prime, and then this is times f. Do y'all see that the way I wrote it down? I still have not taken any derivatives. I've just applied the formula to this. And now each one of these individually you have to look at and see, can you take the derivative? So let's call on somebody. So Cruz, are you here?
Yes, sir.
Okay, Cruz, what have you got for this first piece? The derivative of x squared is what?
It's 2x.
2x, okay. And then I'm going to multiply that times what?
The sine of x.
Sine of x. And you're not touching that, right? You're just leaving it alone.
Mm-hmm.
And then you go plus. Now, Cruz, you're ready to work on the next piece, which is the derivative of sine of x, which is
Cosine x.
cosine of x. And then times what?
X squared.
Squared without taking the derivative. Now, this is correct that, I mean, we're done, but I'm going to rewrite this slightly different. What I'm going to do is on the second term, I'm going to move the x squared out in front of the cosine of x. And the reason I'm doing that is because we all have to understand that the x that's here in the cosine is in a set of parentheses, even though we don't have to write the parentheses. And you are not allowed to multiply the x and the x squared together to get x cubed. All you can do is move the x squared out in front. All right, so that's why I like to slide it out here, just so there's no confusion. You good? Everyone okay with that? Okay, well then I have a challenge for you. I would like you to now find y double prime. In other words, I want you to take the derivative of that derivative that we just got. Okay, so I want us to take y prime, here's y prime, it was 2x sine x plus x squared cosine x. I would like for you to take the derivative of this. So I'm going to help you out to start. Justin, are you there?
Yes.
Okay, Justin, do you see the addition symbol here?
Yes.
Okay, so the addition means that we can do this and this separately, right? Like I can go find the derivative of this. So in other words, I can do the second derivative would be, I need to take the derivative of this and then just add to it the derivative of that. And that's because I have addition, right, Justin?
Yeah, that makes sense.
But Justin, on that first thing you have to take derivative of, do you see what you have between these two?
They're being multiplied.
That's multiplied, right? So you have a product right here. And when you go to do this one, you also have a multiplication that you have to deal with. So Justin, you have to now do two separate product rules, one for the first part and one for the second part. And so I would recommend you call this F and G and then run the formula. And then over here, this is a separate problem, do F and G and then run the formula. I'm going to leave the formulas right up here in yellow. I'm going to give everyone a minute or two to see if you can't crank out the derivative of this piece. Go ahead. I'll give you like a minute and a half, 2 minutes. I just launched a poll. If you could just click yes when you're done. Don't click no, just click yes when you're finished. We have about half of y'all that have done, that have said you're finished. Go another 15 seconds. Okay, that's good. All right, so Jorge, you're up. So Jorge, are you understanding? Do you understand the formula? Do you understand how we got to that last line I put up there? You're on mute though. Just
Sorry.
Yeah.
Yeah, I'm hanging in there.
so help me out with this first one, Jorge. When you apply the product rule to this first product, what are you getting?
I got 2 times sine x plus cosine x plus 2x.
Cosine x times 2x. You said plus.
Okay, yeah, times 2x.
Okay, good. So you've got basically for that f, this is basically f prime times that was g, and then plus this was g prime, and then this was times f. Jorge, that's all good?
I think so.
Yeah.
You tell me.
Anybody have any questions there? Now we have a plus symbol. Did you get the second part, Jorge, or shall I move on to someone else?
I got 2x times cosine x minus sine x times x squared.
Perfect. Okay, the minus, everybody, comes from the fact, not because there was a minus sign here, the product rule has a plus sign, but the derivative of cosine of x is negative sine x. So really, technically, this is what it really looks like. It looks like plus, and then derivative of cosine is negative sine, and then the x squared. But what Jorge did is he just changed the plus minus into subtraction, which is fine. So I'm going to rewrite this. Watch how I write my final answer. 4x sine, no, oops, that's a total mistake. 2 sine x plus 2x cosine x plus 2x cosine x minus x squared sine x. Okay, so all I did here was just brought this down. This 2x, I put it out in front of the cosine. Here, 2x in front of cosine. Here, I brought the x squared out in front of the sine x and put the minus instead of the plus minus. So y'all see we can combine some like terms together. You'll see we have two things that are the same. So we can go 2 sine x plus 4x cosine x minus x squared sine x. That would be your second derivative. Can you imagine what it would happen now if I asked you for the derivative again? You would have a plus sign and a minus sign. So you do each of these three separately. On the first one, is this a product rule?
Yes.
Yes, it is 2 times sine x, but remember 2 is a constant, right?
Yeah.
So it could just come for the ride. So we wouldn't have to do the product rule here. But here we would, because this is 4x times cosine x. So here we would do a product rule. And then here we have x squared sine x, we would have to do a product rule here. I'm not going to do it. I'm just trying to show you, you could keep going with this, right? Okay, let's move on. Let's do this. Okay, new example. So let's say that y is equal to x to the 4th plus 3x cubed minus 2x squared plus 1 times x to the 8th minus 4x to the 4th plus x minus 4. And I want you to find y prime. What's the derivative of this? Now, one thing you could do at this point is you could multiply all this out. What I mean is you could do here to here, here to here, here to here, here to here, then here to here, here to here, here to here, here to here, and then here to there, here to there, here to there, here to there, and then the 1, 1, 1, 1. And you can multiply it all out, collect like terms together, and then take the derivative of each one separately. Because you just have a bunch of pluses and minuses between them, right? You could do that. But you could also realize that you have multiplication right between two things, right? And so you could treat this whole thing like F and this whole thing like G, and then just use the product rule. So the product rule says that I want to do the derivative of this times this plus the derivative of this times this. I'm going to write that down. The product rule says I need to take the first one. I need to take its derivative, then multiply that times the second one without taking the derivative. Then add to that the derivative of the second one. So the derivative of that one times the first one without taking the derivative. So just keep in mind there, I put the little derivative signs there just to illustrate this is F prime times this is G plus this is G prime times this is F. Are y'all following this? You see how this formula works? Okay, is it Bree? I think Bree's up. Are you there, Bree?
Yes.
Okay, Bree. Let's see. What do you got?
Okay, 4x to the third power plus 9x to the second power minus 4x. And then do you want me to just leave out the 0?
Yeah, leave out the 0, but all of that in parentheses, right? Because it has to multiply times this. Am I changing this at all?
No, so just
Okay.
leave this is blah, blah, blah.
Keep it all here. Don't touch it. Just leave it alone. Plus now this one, you do need to do something, right?
So it's gonna be 8x to the 7th minus 16x to the 3rd plus x equals, what was it, 1?
Yep.
1.
Okay.
And that's it, in the parentheses.
And then just copy it, right? Do anything here.
Yep.
That's it. Now, at this point, we are done taking the derivative at this point. So could we multiply that all out? Yeah. Do we want to? No, because it's just algebraically, that's just a mess. That is the derivative. So this unsimplified version of this, I refer to this as the raw derivative, because we haven't done anything to clean it up. It just, there it is, that's the derivative. I use the product rule. Now, if you want me to do something with that, then I might have to do some algebra, but for now, I'm happy with that. And on your exam next Thursday, I'm going to be asking you for just the raw derivative. I'm not going to be asking you to do anything with it, all right? Later on, we will do something with it, but for now, we just want to make sure we can apply the rule. Any questions? So product rule, F prime G plus G prime F. Or I like to think of the product rule not in terms of F and G. I always think of the product rule as the derivative of the first one times the second plus derivative of the second times the first. Derivative of the first times the second plus derivative of the second times the first. Just burn it in, okay? All right, you ready for the next rule? Quotient rule? So if y is equal to some, well, let me do it this way. Quotient. Let's see, how did I write that earlier? I want to make sure I kind of keep with the same format here. Okay, here was the product rule. And if I want to do the quotient rule, here's what it looks like. If you have a function f divided by, this time a quotient, okay, so division, divided by some other function, and you want the derivative, here's what it is. You ready? Now, again, I could prove this, but not today, not in this class, come to my office hours. All right, so here's what it is. It's the derivative of f times g. So far, doesn't that look like the product rule so far? I mean, that's exactly the same as the start of the product rule. Instead of plus, though, you put a minus. And then you go derivative of g times f. So right now, as it looks right now, that is exactly the product rule with a minus in between, right? That's the only difference. There's one more thing, though. You have to take the entire thing and divide it by g squared, not the derivative of g, just whatever g was, square it. And that is your quotient rule. So again, it kind of sucks. It's like if you have y equals, let's take x squared over sine x instead of x squared times sine x. In some other universe, you wish that the derivative was just this. You see, all I did there was took derivative of the top and bottom separately, right? And that's the answer. Nope, that's not the way it is, okay? And I always tell my students that if this was the way it was, and then back when I was showing you the product rule, remember I said, wouldn't it be nice if the derivative of this was just 2x times cosine x? If that were the case, calculus would be a much easier class because it would just be kind of intuitive the way you take derivatives. Everything starts to get messy once we get to products and quotients. That's when things start to become complicated. So when I'm looking at this problem, if I want to know the derivative of it, I need to identify that the numerator, I can call that f, the denominator, I can call that g, and then following this rule, it'll be, the derivative will be the top, its derivative times the bottom, minus the derivative of the bottom times the top one, which is f, which is x squared, and then all of that over the g function, which is sine of x, but all of it squared. So can you all see that formula in here? Can you all see this quotient formula in the way I wrote it out here? Everybody see the f prime times the g minus the g prime times the f over the g squared? See all the pieces? And now we just need to crank it out. So the derivative of this would be, okay, I need the derivative of x squared, which is 2x times sine x. And then I'm going to subtract from that the derivative of sine of x, which is cosine of x, times the x squared. And the whole thing divided by sine of x squared, which another way to write sine of x squared is to write sine squared x like this. That's the same thing as this. These two, this and this mean the exact same thing. And that's done, but maybe one thing I would want to do is just again move that x squared up in front of that cosine so you don't accidentally put those together. And there's your raw derivative. What do y'all think? So let's not lose appreciation for what we've actually just done here with these rules. I'm going to go back into a graph. The function that we just looked, that I just put in here was x squared over sine x. Very unusual looking function, right? Would you all agree that's strange? It's a weird looking function. So let's say I wanted to go somewhere on this function and figure out what the slope of the tangent line was. I would need to know its derivative. Now, the derivative that we just got was 2x times, oh, wait a minute, hold on.
Yeah.
I just realized that that was a 9. Okay, oops. So that function is not as bad. Oh, there it is. Okay, so it looks weird still, but just not, it wasn't that. So the derivative of that was that sine x minus x squared times cosine of x, the whole thing over sine x squared. Whoa, okay, that's nuts. So if I wanted to know what the slope of the tangent line was for the red curve, let's say I went to right here, some value of x, and I wanted to know what the slope of the tangent line was right here, it would be equal to the y value right here on the blue function. Whatever the y value is of the blue function is what the slope of that line is on the original function. And you can see it's actually kind of cool. Look what's happening here. Right here at 0, look at the slope of the tangent line there. Doesn't that look almost like a perfectly diagonal line? Which would have a slope of what? It was perfectly diagonal. It would have a slope of 1, wouldn't it? And look at the y value of the blue function there. It's 1. It matches the slope. Can somebody tell me if the blue function hits the graph here, if it hits here, it goes through here. Can you tell me what the slope of the tangent line on the red function must be then? There?
1. 0.
0.
0, right? Which means that we should have like a lowest or highest point. Yeah, exactly. So let's go look for the red function. Where is it? Where is it? Oh crap, we're not gonna be able to see it. Shit. Okay, I'll go to a different one. How about we go right to that value. If we follow that straight up, okay, if we follow that straight up, can you see that it corresponds to, come on, what's going on here? I can't, oh, there we go. Okay, clear. If we follow this straight up, you can see that that up here is where the slope of the tangent line is 0. And you can see that's the lowest point on our graph right there, and it corresponds to the x-intercept of the derivative. So big picture is this. If I wanted to know, if I were interested in knowing where that graph has highest and lowest points, these peaks and valleys, I would have to take its derivative and do what with it? Figure out where it's what?
Plug in 0.
Where it's equal to 0.
Oh, yeah.
I would have to set that equal to 0, which means I have to be able to solve this equation. And that might be a hard equation to solve. But we're going to do that later. We're not quite there yet. But again, I'm just trying to make sure we're not what's the term, missing the forest through the trees? Is that the right way to say that? I don't want us to miss the forest through the tree. Is that right?
Wouldn't it be missing the trees through the forest?
Yeah, through trees through the, I don't know. Either way, don't lose sight of where we're going with this. Okay. Before I give you another example, I want to point something out. If you go to your formula sheet, these formulas are here. Okay, the quotient and product rules are in your formula sheet. But I want you to look at the first one for product rule. Okay, the way that the book has this is a formula sheet out of your book. This is the way the book has it written. They write f times g prime plus g times f prime for the product rule. That is not the way I presented it to you. I presented it as f prime times g plus g prime times f. So first, I want you to just realize that these are the same things, because this and this are exactly the same, because multiplication, it doesn't matter what order you go in. And these two are also the same because the order doesn't matter. And because we're adding, you can move them around and that doesn't matter, right? Y'all see that? So you might ask, why would you show it to us that way if the book in my formula sheet shows it to me this way, right? That seems like a fair question. Well, I have a good reason for it, okay? I want you to now, I want you to now look at the book's version of the quotient rule. Okay, so I'm gonna write this down. You know what? I'll do this. Let me just copy all this so I can write this on a different page. Students always get mad at me when they realize that the formula in the book is different than the formulas I'm giving them, and they get all upset. I mean, not everyone, but you know, people are like, "Why are you doing that?" I have a very good reason. So, okay, so here's the book's version of the product and quotient. So the book's version again for product is F prime, I'm sorry, F times G prime plus G times F prime. My version is F prime times G plus G prime times F. That's mine. This is the book, right? Okay, let's look at the book's version of the quotient rule. It is G times F prime minus F times G prime all over G squared. That's the book's version of the quotient rule. My version of the quotient rule is F prime times G minus G prime times F all over G squared. Can anybody see why I teach it the way I teach it?
Because otherwise
More.
you'd accidentally do the wrong one. Because with multiplication and the adding, it can go either way. But because it's subtraction, it could really throw you off.
Yeah.
And
Someone
so-
have another comment on that?
Well, because it keeps the F primes together on the same side versus having them on different sides. Again, with the whole subtracting throwing you off and all that.
Yeah. So remember when I was showing you the quotient rule? Do you remember when I started writing it out? I said, hey, doesn't this look like the product rule? Isn't that what I said? Except that there's subtraction and divide by G squared, right? That's the only difference. The only difference between my formula here is there's a plus here, there's a minus, and then of course the G squared. That's the only differences in the formulas. But if you look at the book, look, this right here is not the same as this, right? Like that, you would have to remember to do this one first, then subtract that one. So it's almost like you're changing everything, right? You see how it doesn't like match up very well? So as long as I've been teaching calculus, well, actually, when I was a student of calculus, I realized that, at least in my mind, it made sense for me to memorize this and then just remember a couple of little slight changes for the quotient rule, as opposed to thinking about it as like almost like two completely different formulas. They're not completely different. They're very similar if you look at them a certain way. So when I'm grading tests, when I'm grading your tests, I can always tell the students who have gone to a tutor or who have maybe learned this in a different, you know, maybe they took calculus already in high school or they're taking this class again. I can always tell who those students are because they always are these two formulas because that's what they've been taught. And then I can tell which students are seeing it for the first time and are using the way I'm showing. So I don't care as long as you get the right answer, but I always kind of make a little mental note like, okay, this student has done this before, or they're going to a tutor for help. Tutors will never use the formulas I use because, well, at least I've never met a tutor that does, unless they took me and then they would maybe do that. So anyway, okay, I just wanted to point it out in case you're looking at the book and you're like, wait, these formulas don't look the same. They're going to look different, but they're the same thing. Give me the same answer. Okay. You all ready? We're going to turn the screws. That's a figure of speech. You all have heard that before? Turn the screws. Where does that come from? You all ever heard that before? No? So in medieval times, when people would get in trouble and they would torture people, right? They'd put them on this thing like called the rack, you know, where they stretch them out with ropes, and they'd start turning this thing and just start stretching them out. Tell us everything you know, right? Or they put their head like in a vise and start turning it and start squeezing their heads until they gave up, like, where's the secret location of the weapons or something, right? They torture people. The idea of turning the screws is basically it's time to make this harder and harder and more difficult, all right? So here it is. Here's your first kind of like step up from what we've seen. It's not going to be a huge step. I'm slowly turning the screws. So wait, we did that already, didn't we? We did that problem? X squared sine? Okay, so I want to add this element to it. I want us to divide that by x cubed plus 1. All right, let's just look at it first and think about it. So what do you see? Because it's very important in a class like this for you to see what you're working with, because you can't do anything unless you see like physically what's in front of you so you know which path to go down. So what are y'all seeing?
I see the x squared being multiplied with the sine x on the numerator.
Okay, so you're seeing, Jair is seeing a product right there. Is everyone seeing that product? Okay, good. Anything else you see?
The sum underneath.
Okay, you have a sum underneath.
And you have a constant.
You have a constant, good.
But it is definitely smelly. Not the good smell.
What about this bar?
Oh, quotient rule.
You've got a huge division here, don't you? You've got this big division. Now, if you look at this division and kind of like just isolate your brain to think about the numerator by itself as being f and the denominator by itself as being g. Do you all see ultimately here we have a quotient, big quotient. Now in the numerator you have a product, but we'll get to that. The big thing is to see that we have a quotient, right? And so if I want to know what the derivative of y is, I know that I must apply the quotient rule, which is f prime times g minus g prime times f all over g squared. That's ultimately the big picture of what's happening here. So let me write down what that is. F prime is the derivative of the top, right? That's what it means. So I'm going to write that down. It's whatever the top is, take its derivative. That's f prime. Then I have to multiply that times g, which is the entire denominator. So multiply that times the g here. Don't touch the g, right? The product or the quotient rule says the g is just g. The only thing that you're going to take derivative of here is the f. Then we subtract. Now the g prime. Now you're going to take derivative of the bottom. So we're going to do x cubed plus 1 derivative. Okay. And then don't touch the top, right? Which is going to be the x squared sine x. Everything divided by g but squared. So x cubed plus 1, that whole thing squared. Y'all good? We still have some derivatives to take, right? So let's see, Brian, are you there? I see you there.
Yes.
Brian. Okay, so Brian, I saw you shaking your head, so you seem to be okay on this. Brian, we only have 2 derivatives we have to do right now, right?
Yes.
2 different derivatives. Which of the 2 derivatives is easier?
I
I mean, I think it's the right side because one just goes to 0.
Yeah, this right here, if you were asked to take derivative, because there's addition between them, you can just do them separately, right?
Mm-hmm.
So the derivative of x cubed would just be
2x over, or yeah, 2x squared
3. Bring the
or 3x. Yeah, 3x squared. Yeah, 3x squared.
and then plus the derivative of 1, which is 0, right? So
0, yeah.
3x squared. That one's going to be the easy one. Y'all see that? Y'all agree? I'm just kind of thinking through this right now. I'm not writing anything down. I mean, I am writing something down, but the red is my thought, okay? The red is what I'm thinking there. Now, what about this, Brian? When you look at that, what are you thinking?
It's gonna be, it's a multiplication, so you'd have to do the or that's the product rule.
Okay, so that means you're going to have to run the product rule on this, aren't you?
Mm-hmm.
That means you're going to have to treat it like it's its own problem. So what I'm going to do is on the side over here, I'm going to do a little scratch work, SW. It's a little scratch work to figure out what the derivative of x squared sine x is. Whatever this answer is going to be what this gets replaced with. But all this other crap is still going to be here, okay? So this is going to be a very ugly looking answer when we're done. Y'all see that? So the derivative of x squared sine x would require the product rule. And I'm going to go on to Roger. If Roger's here. Is Roger here? Gabriella?
Yes, sir.
Okay, we've already done this one, but I want to see if you can just run me through this real quick. What would the derivative of this product be?
Wouldn't be 2x sine x plus x squared cosine x.
Yep. Good. So that right there, we've already done it. You can look back in your notes, but we want to get to the point where you can do this mentally, if possible. Derivative of the first one, 2x times the second, plus derivative of the second one, which was cosine x times the first one, x squared. Now, Gabriella moved the x squared out here in front, which is fine. Okay, I think we're ready. This is going to be equal to this top left, which is the derivative of that, which is everything that Gabriella just said. It's 2x sine x plus x squared cosine x. That's just the top left corner. We still have to multiply that times x cubed plus 1. Minus, now Brian and I went through this one right here kind of mentally and figured out that the derivative of that's just 3x squared. And then we still have times x squared sine x. And then the whole damn thing is multiplied by or divided by x cubed plus 1, everything squared. Oops, squared, not cubed. And that is your derivative. It ain't pretty, but it's the derivative.
With that, could you just cancel out the x cubed plus 1 on the top and then just leave it over x cubed plus 1 instead of squaring it?
You could only cancel out this x cubed plus 1 if there was another one over here.
Okay.
In both. Now, what you could do is split it into 2 fractions. So you could take all of this over that and make a fraction out of it, and then take all of this over that and make a separate fraction. And in the yellow fraction, you could cancel one. But you couldn't do it right here. Like you can't just go like, oh, that goes away and that becomes a 1.
Because then if you bring it back together, you would have to bring it back that x cubed plus 1, right?
Yeah, when I was a math student, I had trouble with these same little things. I always try and convince myself using an example, like I got something times something minus something times something over something. So I would write down 5 times 4 minus 3 times 7 over, let's say 4. Am I allowed to cancel these 4s? Well, I don't know. I have to convince myself that that's true. So let's see. If I don't cancel anything, this is 20, take away 21, that's -1 over 4. Y'all see what I'm doing? the correct answer should be -1/4. But if I cancel these, then I get what on top? 5 take away 21/1 because it went away. So I get like -16. Something's wrong here. Okay. I'm just showing you that's when I was an algebra student, I always try to convince myself of things by putting numbers in for things and seeing if it came out right.
All right, so if you were, so in order to ever cancel something out, like there's like an actual equation, like how we have it right now on top, and then there's only one like simple equation on the bottom or so, it would have to be something you'd be able to factor out from each of them.
Exactly. You would have to be able to factor it out of both the top and bottom. I mean, sorry, factor out the top and then cancel with the bottom. Kind of like the H when we were doing limits and we were able to pull an H out of everything and then cancel it. You can't just cancel an H if not everything on top has an H. Everything on the top had to have an H for canceling to occur. All right. You seem like you're ready for more. Y'all seem pretty excited about this. I'm kidding. Here we go. How about this? Sorry, I'm contemplating how I want to do this. X cubed times sine x over x cubed plus sine x. These signs can't cancel. These x cubes can't cancel. If you want to convince yourself of that, replace those with numbers. Right? This is 28 over 11. If you start canceling stuff, you get like the 4's cancel. I don't even know what the hell you would get here. Like, I'm not sure how your brain would do this, but maybe you get like 1/1 + 1. Maybe you get 1/2 or something. I don't know how you would do the canceling here. It would be wrong, but it's not 28 over 11, which is the correct answer here. So no canceling. All right. Enjoy. I'll give you 5 minutes. Maybe 4. See how about we do a poll? You let me know when you have an answer. I'm going to relaunch the poll. Just let me know when you're done. And just get the raw derivative. You don't have to clean anything up. Just make it nice and ugly looking. I know y'all are working, but I'll just tell you, remember in the beginning of the semester, I told you there are certain calculators you cannot use The reason is because those calculators, you could just type this function in and you could ask it to take the derivative and it would do all this for you. I've placed the answer up here. If you want to look at it, you can. We're going to go another minute. Yeah, most of y'all are done. While you're sitting there, I'm going to show you the next problem so you can start thinking about it. All right, does anyone have any questions over the first one here in black about where any of this came from? Now's the time.
I have a question.
Yes.
Okay, so I see, so you have f prime right there. You're still supposed to find the derivative of that, right? Like you keep going.
The derivative of f, right? So this is f, and you have to take its derivative, and that's this. I didn't show the work, so I had to use the product rule on this.
Okay. See, I had that, but I just kept going. Like I guess I found like the derivative of that, like the second derivative. I kept going because it confused me, so I didn't know when to stop. Does that make sense?
No, I'm not following you. Say again.
So I found that, like I found that derivative, like
Okay.
of the entire that, but I kept going, so I guess I found like the second derivative of the entire equation. I just
So you
didn't know
did
when
the
to
derivative
stop
of this
because I
again?
thought. I'm sorry.
You did the derivative of this again, a second time?
Yes.
Okay, yeah, so in the formula, you just need the first derivative, that's it.
Mm-hmm.
That's all you need. And then it's times the bottom, whatever the bottom is, goes here. I guess I'm trying to figure out, why did you take the derivative again?
I must have written it down wrong, I guess. Because okay, you're supposed to take the product rule for the numerator, right? And then first, like for the okay, I think I get it. I think I messed up in my head somewhere.
Maybe you're confused because in this problem that I had done, the first product rule problem I had done, we did the product rule and then I asked y'all to do the second derivative. Maybe you're thinking that that has to happen each time. That was just to give you an example that we could take a derivative again. In the actual rule, we just need the first derivative here.
Okay.
Any other questions on this? So what's wrong with this problem here? What's different? There's something very different here.
There's 3 things being multiplied.
There's 3 things being multiplied. And the product rule only deals with when you have 2 things being multiplied, right? So watch how I'm going to do this. This is tricky. I'm going to look at the first product I have here, and I'm going to call this F, and I'm going to call everything over here G, all right? That's fair, right? I can do that? So according to the product rule, the derivative of this should be F prime times G plus G prime times F. That's the product rule, which means I have to take the derivative of F. So I'm going to take the x squared plus 1, take its derivative, and then multiply that times what? What am I multiplying that by?
Times G, which is sine X times tan.
Let me write down G. Here's G, right? So this is F prime times G. And then plus, now I need the derivative of G, right? So I take sine X tangent X. I need to take its derivative and then multiply that times F, which is the first function. Do you all see that? F prime times G plus G prime times F. Y'all see that? What about F prime? Is that going to be easy? Derivative of x squared plus 1? Yeah, that's just what, 2x? But what about the derivative of G? What's that going to require? Well, G,
Another product rule?
Product rule?
G is a product, which means I'm going to have to do a product rule for this to take its derivative, which means I'm going to have to go over here on the side. I'm going to have to figure out what the derivative of sine of x times tangent x is. And I'm going to do a new f and g being multiplied and then apply my product rule. So when I do the derivative of f, I get cosine x times g plus derivative of tangent x, secant squared x, times sine x. The derivative of tangent, I gave that to you in our notes a minute ago, right? So I told you what derivative of tangent was. That piece here is what this becomes.
Where is it? Secant squared x.
I'm going to go 2x sine x tan x That's just all of this. Take the derivative of x squared plus 1 is 2x, then multiply times this. Plus, now all of this in yellow gets replaced with cosine x, tangent x, plus secant squared x, sine x. But then all of that gets multiplied times x squared plus 1. And that would be it. All right. Y'all doing all right? So, I mean, really what this comes down to is that you now have formulas to use to take derivatives. It's like I've taught you how to use a hammer and a saw and a drill, and now I'm going to ask you to go build something. So the homework is where you go build it. And the only way to get good at it is to practice, 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 practice. You can't just watch me do it and be like, yeah, I get it. Okay, you have to practice. All right, here's another example, very weird one. Let's let y be equal to x, x cosine x. And I want us to find y with a 5 up there. So what does that mean? What does that notation mean?
The fifth derivative.
Fifth derivative. And then let's call that part A. And then for part B, I'd like you to find the 532nd derivative. All right. Let's do part A first. Okay, let's do part A before you start freaking out about part B. Here we go. Derivative. All right. Let's see. Marissa, are you there? Oh, wait, Marissa, you participated, but I'll have you go here. Let's see, Marissa. If I ask you to take derivative of this, you see the product, right?
Mm-hmm.
Okay, so that's f, that's g. So go ahead and just tell me what the derivative of that would be. See where you are.
So it's going to be 1
Times.
and then multiplied by cosine x.
Okay.
Plus
Okay.
x. And
Okay.
then by multiplied by negative sign.
Negative sign. So notice how I put it in parentheses, Marissa. I did that because if you don't put the parentheses, it'll look like x minus sine x, but it's actually x times negative sine x. So that means that our next line, we can get rid of the 1 and we can put minus x sine x here. Is that all right, Marissa?
Yes.
Good. Okay, we've got the first derivative. Jair, you get the second one.
So this would be cosine x. That's negative sign.
Okay, so you have subtraction, right, Jair?
Oh, yes.
So you can do these individually, right? You're gonna be able to do these individually. So let's do this one first. You said the derivative of cosine of x was what?
Negative sine x.
Okay. And now be very careful here, Jair and everyone else. Y'all see the minus sign there, right?
Mm-hmm.
Okay, you're gonna subtract from that whatever the derivative of this is. But Jair, do you see the product?
Yes.
Okay, that means when I use the product rule, it's going to become multiple pieces because the product rule has an addition sign. So I must put everything I get here for the product rule, I must put it in parentheses so that this negative distributes through. Does that make sense, Jair?
Yes.
Okay, so go ahead, give me the product rule on this piece.
So it would be 1 times cosine x.
Remember, you took derivative of the x, right? To get the 1, you leave the other one alone.
Oh, that's true. Yes, Sophie.
Okay, so sine x.
Okay, and then
plus
the derivative of g would be cosine.
Yep.
And then
one more thing at the end.
And then x.
Times x. Good. All right. Okay, let's clean it up. This is negative sine x minus sine x minus x cosine x. So what happened here was I had a minus sine x, this minus went through, turned this into a minus, minus went through, turned that into a minus, and I moved the x out front. This gave me negative 2 sine x minus x cosine x. And that's because I can put these two together because they're the same, right? All right, there's our second derivative, everyone. 3 more to go. All right, Nathan's up. Nathan, you there?
Yeah, I'm here. Sorry.
All right, so Nathan, you see the subtraction sign between these, right?
Yes.
You can do them separately. So start me out with the first one. What are you going to get for the derivative of this?
It would be negative 2 cosine of x because the 2 is a constant. So you
Yep.
can put that separate. So then it's just, yeah.
Very good. So look, everyone, Nathan noticed that, yes, you could try and act like this is a product, but negative 2 is a constant attached to the function. So it can come for the ride, and then you just take derivative of sine. Now, Nathan, on the next part, you have the minus sign again, right? And then, Nathan, you see that product, right? Right there?
Yes.
So you're going to need a parentheses again, and then go ahead and crank out the product rule on this.
So it'll be 1 times the cosine of x
Mm-hmm.
plus, let's say, negative sine of x
Good.
times x.
Times x. Good. All right. Y'all are doing good. Negative 2 cosine x. Cleaning up. Minus cosine x plus x sine x. So the negative goes through here, makes that negative, but the negative hits that negative, becomes a plus, and then you have the x in front of the sine x. And those cosines come together to give you negative 3 of them, and then you have plus x sine x. 3 down, 2 to go. So this was our first derivative. This was our second derivative. This is our third derivative. And for the fourth, I'm just going to do y with a little 4 in here. All right, Brandon is up. Brandon here? I don't see Brandon. No Brandon. Okay. Cody. I don't think Cody's here either. I think Cody told me he's not going to be here today. All right, we're back to the front of the line. So, any volunteers?
I'll go.
Go ahead.
So the derivative, so since it's a product,
Mm-hmm.
it would be, oh, it's a constant, so that would be negative 3, so be positive 3 sine x.
Good, good. Okay, so you see how that negative and the negative sign is going to make a 3 sine x here? Good. So everyone's, this is negative 3 comes for the ride, but then the derivative of cosine is negative sine. So you've got a negative 3 times a negative sine, which gives you positive sine of x. Plus, okay, you want to keep going?
Yes, so that's another product rule.
Need parentheses. And now go ahead.
It would be 1 sine x,
Mm-hmm.
and then plus cosine x.
Times.
Cosine times x?
Cosine x, did you say times x?
Yes.
Okay, so look, have y'all noticed that we already did the derivative of x sine x, that we already did that earlier? Y'all see that? We did it up here, and we got this answer right there. I could just paste that in there since we did that earlier. We're going to start to see a pattern, everyone. Pattern is developing. So I distributed a positive this time and just leaves everything alone. And now I get 4 of these, 4 sine x plus x cosine x.
Okay, let's check the map to see where we're going next. This is the last island.
All right. Do y'all see any patterns? The first derivative.
Yes.
Yeah, that first derivative had a 1, and then it was cosine, and then it had minus, oh wait, here it is right here. It had cosine x and then minus x sine x. The second derivative had -2 sine x minus x cosine x. So it went from cosine x to -2 sine x. Let's just, you know what, let's just look at the first piece. It went from cosine to -2 sine, then it went -3 cosine, then it went 4 sine. Do we have any guesses as to what the next one would be?
5 cosine.
Sine.
Positive or negative?
Positive.
What do y'all think? We went positive, negative.
Is it going to be a negative?
Oh, negative.
1, 2, 1,
It
2.
would be a positive because cosine goes to negative sign, so wouldn't sine. I mean, even in the thing.
I think it goes positive, negative, negative, positive, negative, negative.
So when positive, it looks like it's negative, negative. The next one was positive, and then if we take derivative of that, we should get a positive, right? So I'm guessing that the next one's going to be a 5 cosine of x. And then any ideas on what this will be? Let's see what the second piece is doing. It was minus x sine x. Now it's minus x cosine x, then positive x sine x, then positive x cosine x.
So it'll be minus x sine x.
Minus x sine x? It's kind of like we're asking a question, is that what's happening? You know, like maybe it is. The only way to check it is to take the derivative, right, and check. If we continued with this though, what would the next one be? The sixth one, if we had the pattern right, the sixth one would be a positive or a negative?
Negative.
Looks like we have, yeah, again, forget the first derivative, start from the second one. It looks like negative, negative, positive, positive. Then we should have -6 sine x, it's going to switch. And then what about this next sign right here? What are we going to get for this?
A positive.
Positive, negative. What do you think?
Here we go.
Negative, negative, positive, positive. Maybe negative, negative again?
Negative x cosine x.
Cosine x. Again, the only way to check it would be to actually do these derivatives. But we have the right, this is the right pattern. Let's keep going. What would the seventh derivative be?
It'd be positive 7 cosine x.
Positive or negative? These numbers keep going up, right? It was like 1, 2, 3, 4, 5, 6. This should be a 7, but we should have a negative in front because the pattern is that it's negative, negative, positive, positive, negative, negative, positive, positive. Like if I keep doing this, the next one would be 8, 9, negative 10, negative 11, 12, 13. Are you following what I'm doing here? Negative, negative, positive, positive, negative, negative, positive, positive. And then these are just going to switch back and forth. So this should be cosine x, sine x, cosine x, sine x, cosine x, sine x, cosine x. And then what about the next piece? Negative, negative, positive, positive. Negative, 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 positive, positive, negative, negative, should be positive, positive, negative, negative, positive, positive, negative, negative, and switch. And then these just keep flipping. X sine X, X cosine X, X sine X, X cosine X, X sine X, X cosine X, X sine X, and so on and so forth. This would be the 13th derivative. Okay. We're not done, okay? But you can see how a problem like this, the main thing here was just to practice with it, but really that you can start developing patterns with certain functions. You can start to see patterns. Let's check this answer. I'm going to go to Wolfram Alpha. I want to know the 13th derivative of X times cosine X. Let's see if it can do this. 13 cosine X minus X sine X. 13 cosine X minus X sine X. So it looks like we've got the pattern right. All right. Any questions? We haven't done part B, but are there any questions?
No.
The pattern starts on like differently for both, right? So the pattern for the left side doesn't start until the second one?
Yeah, it
and
looks
then,
like it starts at the second one.
And the pattern on the right side starts off the rip, the first one, right? Okay. Okay, thank you.
So let's try and take a guess as to what this would be. Well, how about the number? Are we confident that the number is just going to be, the number is the derivative we're doing? So are we pretty confident that this derivative will be, it'll have a 532, right? That much I can say. Now we have to determine if it's going to be a sine or a cosine here. What do y'all think? Is it going to be a sine or a cosine?
Sine.
Why sine?
Because it's even.
Because all the even ones have sine. Do y'all see that all the even derivatives have sine? Cosine's odd. 4 sine, 5 cosine, 6 sine, 7 cosine. So I know that all the evens give me sines, and this is an even number, so I should have sine X here. Look, this is what I don't know right now. I don't know if this is a plus or a minus. I'm not sure yet. And then this next piece, I don't know if this is a plus or minus either. I don't know. But what would the last piece be? It's either an X sine X or an X cosine X. Which one is it?
Cosine.
Cosine, again, because evens, all the evens have cosines. So I know I'm going to have an X cosine X here. So are y'all with me with the idea that all we really need to figure out is whether or not it's plus or minus for both of those? But just figure that out. Okay,
Yes.
Here comes something kind of strange and unusual that you probably have never seen in your life. All right. So I'm going to do this. Computer science people out there may have seen this. This is real important in computer science, though. It's called modular arithmetic, or mod. Okay. So here's how mod works if you've never seen it. Let's say I write down 13 mod 2. Okay, what this means is take 13 and divide it by 2. Okay, so what's 13 divided by 2? Well, 2 goes into 13 6 times. That gives you a 12. You subtract, and your remainder is what? What's your remainder? How much is left over? 1, right? You have a remainder of 1. So 13 mod 2 is equal to 1. The 1 is always the remainder that you get. So if I do 13 mod 2, I'm really saying to myself, what's the remainder when I take 13 and divide by 2? What's its remainder? Let me give you another one. What's 14 mod 2? Take 14 divided by 2. How much do you have left over?
0.
You get 0. Let me give you another one. What's 13 mod 3? So how many times does 3 go into 13 evenly? Goes in there, what, 4 times? But you would have how much left over?
1.
1. Okay. What's 14 mod 3? So 3 goes into there also 4 times, right? But how much do you have left over this time?
2.
2. Okay, so you have 2. What's 15 mod 3?
0.
0. When you do modular arithmetic, okay, this is the important thing. When you do modular arithmetic, here's 2 different examples. When you do modular arithmetic, whatever your number is here represents how many different answers you can possibly have. So if you do something mod 2, there are only 2 answers that could possibly come out, 1 and 0. That's the only answers possible. If you do mod 3, there's 3 answers possible, 0, 1, and 2. If you do mod 4, you have 4 answers, 0, 1, 2, and 3. If you do mod 5, the only answers you could have are 0, 1, 2, 3, and 4. Understand how modular arithmetic works? Kind of.
I was going to say, yeah, we do that in the coding because it's just that the Theatra use the, instead of using the slash, you use the percentages for the remainder quotient.
Yeah.
Or not the quotient, yeah.
Yeah, it's used in programming quite a bit. I actually used it today because I was programming something strange. I found a way. I have a Fitbit watch.
Mm-hmm.
Anyone of you, I'll just show this to you because why not? So if you have a Fitbit watch, you can go to this thing called FitFace, and you can actually create your own watch faces however you want. You can design them yourself, okay? And I have this watch face that I'm developing. My eyes are going, so when I don't have my reading glasses on, it's real hard to read. So even without my glasses, I have to like back my watch away. So I made this really big thing where I can see all the numbers. And when I tap the face of the watch, my screen changes. So when I tap it, it changes to just steps, then heart rate, then the date, then back to the main screen. When I'm tapping, when you tap the screen, let's see, hold on. I'm going way beyond what I need to be doing right now.
It's your heart rate, 180, is it 196?
Oh, this is not. No, this
Oh,
is,
okay.
This is a thing. In this thing, you can do a slider to change all the values so you can kind of see what it looks like in different scenarios. Yeah, my heart rate's not 200 right now. I get really into calculus, but not that much. Okay, so hold on. I have a point to this. Hold on. Okay. And that white so you can see it. All right. So y'all see that little number 4 right there? Every time I tap my screen on my watch, in the background there's a counter, and every time I tap it, it changes numbers. Okay, see it going up? What I have told this program to do is it has
by the Theatra, yeah.
It has 4 different screens it can show me. It can show me the main screen. It can show me the main screen. It can show me, when I tap it again, it shows me the next screen, and then the next screen, next screen. The way it knows which screen to do is this simple code right here. This code right here says, take this number, whatever it is, and do you see the percent sign? The percent sign is mod. So it's taking this counter number and it's modding it by 4, which means the outcome is either a 0, a 1, a 2, or a 3. 0, 1, 2, 3. Those are the 4 screens I have. So as I tap, it spits out either 0, 1, 2, 3. And depending on those answers, it's going to bring up either screen 0, screen 1, screen 2, or screen 3, which corresponds to the 4 screens I have. So as I tap it, it starts flipping through the screens. That's modular arithmetic in action. I mean, that's a stupid, simple example, but it's used all over the place in math because, in computer science, because you can always create a counter and you can always do mod to that counter and get as many results out as you want that continue to cycle over and over and over. Okay.
Okay, so those 4 screens can be compared to those 4 equations because there's 4, so you're just switching in and out of them.
Yeah,
right?
yeah. So what we want to do here is I want to see if there's a pattern. So look at the let's start with the second derivative. Okay, let's try and figure out this sign right here. Let's try and figure out what that sign is. It goes minus minus, right? It goes when I take the, let's say this is the derivative and this is the sign. When I do the when I did the first derivative right here, the sign in front was positive. The second derivative, it was negative. Third derivative, it was negative. Fourth derivative, it was positive, right? And then it went fifth derivative positive, then sixth derivative negative, negative, positive, positive, right? So my question to you is, what do these have in common? 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 So think about the mod on this, okay? Think about modular arithmetic. If you take, let's look at the 8 and 9 first. What would happen if I mod both of those with 4? So what if I do 8 mod 4? What do I get?
You'd get 0. So you're going to the equation that you started with, right?
Yep. And if I do, 9 mod 4, what do I get?
1.
So you get first derivative.
What about this one right here? What about if I do 7 mod 4? What do you get as a remainder? 3. What about 6 mod 4?
2.
You get 2, right? What if you do 5 mod 4?
1.
And
You get 1. What if you do 4 mod 4?
0.
You get 0, right? Look at what's happening at all the pluses. At all the pluses, what are the 2 mods that are coming out?
0 and 1.
0 or 1, right? And at all the negatives, you can check if you go back and do these. At all the negatives, you're getting 2 or 3 for the negatives. So if I want to know what's happening at 532, I would like to do 532 mod 4. So you might need a calculator for this. Does it go in there? 532 divided by 4. Oh, it goes in there exactly. There's no remainder. So if I do that, I get 0. What does that tell me? What happens at zeros?
it's a positive.
Pluses. Okay, so I can tell you this now is a plus. Now I need to figure out this other one. So look, I would never test you on this. I'm just, this is something to show you just how things can really start getting weird. What about for this sign? It was on the first derivative, it was negative, and then second was negative, and third was, first was negative, second negative, third positive, fourth positive, fifth negative, right? Sixth negative. So when we mod 4, I'm sorry, let me write it down. This is for the second sign I'm looking at here. The first, these are the derivatives, and this is the sign. Third, fourth, fifth, sixth, seventh, eighth. Okay, so we said for first derivative it was minus, second was minus. Minus, minus, then plus, plus, then minus, minus, then plus, plus. And if we do our modular arithmetic on these, I'm not going to repeat this table, but we would get 0, 3, 2, 1, 0, 3, 2, 1. So anytime you have a plus sign, that's either a 3 or a 0. Or if you have a minus sign, it's either a 1 or a 2. What do we have for 532? What was 532 mod 4?
0.
0, so our sign should be plus. So this should be a plus. Let's check with Wolfram. The 532nd. Oh man, I got rid of it. 532nd derivative of x times cosine of x. Oops. (532) cosine x. Uh-oh. Oh wait, no, they didn't do that. 500. They did 532 times the derivative. 532nd. Let me try that. See if it's smart enough to know that. Ah, it did. Okay. So it should be 532 sine x plus x cosine x. 532 sine x plus x cosine x. All right. Wow. Okay, we went off the rails there a little bit. It's okay. Got about 20 more minutes. So now I'd like to give you a final problem to work on let's do this. We'll do groups, okay? And this is kind of bringing everything together now into one type of problem. So I'd like for you on this to find the equation of the line which is tangent, oops, to the curve f of x equals x cubed plus x over 3x squared plus 1 at x equals 1. All right. So what I'm going to do now, we have 22 minutes. What I'm going to do now is I'm going to put you in breakout rooms. You'll work together. I'm going to make this a quiz. This quiz will be due by Tuesday before class. All right. And what I'm going to do is I'm going to send everybody a link right now while you're doing the quiz. I'm going to send everyone an email through Canvas, which will give you a Dropbox link to send your work to. Everybody has to turn in their own work. Okay. And this will be a quiz grade, but I'm letting you work together on it. So I'm encouraging you in the breakout rooms to work it out. Look, at the end, just remember what we're looking for. The equation of a line, okay? So your final answer should be the equation of a line. Any questions on that? You've got about 20 minutes to work together. It's due before we meet. So we meet at 1 o'clock on Tuesday. It needs to be uploaded to the Dropbox by 1 o'clock. I won't accept it after that. Okay, I'm going to put you in the breakout rooms and I'm going to hang out in the main session. So feel free to step back in. If you're one of those people who don't like other people, then I'm not going to force you to work together. Let's see here. No, I can leave the same breakout rooms if y'all want. It'll be the same people that were there before. Should be open. All right, everyone, have a good weekend. If I don't see you between now and then.
Excuse me, Professor, are you still there?
I'm here. What's up?
Can we go over a problem, please?
Can you do what?
Can we go over a problem real quick, please?
Yeah, what's up?
I had kind of I don't know if my camera's on. I had asked you about it earlier, but I'm still kind of confused. It was y equals x to the third power and then sine x over x to the third power plus sine x.
Yeah, I could tell that you were still not quite. Where is it? This
Yeah,
one.
because like I understand. Yes, I understand the process. I'm just kind of a little confused. So what I did, I did the product rule for the top, and after I got that answer, I plugged it in for the quotient rule.
Is this the problem or is it a different one? I feel like it was a different one. No?
No, it's that one.
It's this one?
Mm-hmm.
So you looked at the top and you did the product rule on that?
Yes.
And you got 2x sine x plus x squared cosine x.
I got, is it this one? I got 3x squared sine x plus 3x squared cosine x.
Okay, let's see. Is there any way maybe you could?
Oh, okay. I understand what I did. I put my exponent was a 2, or it was a 3 instead of a 2.
Right there. Okay, but let me just double check because I thought this is the problem. Okay, this is the problem you're talking about. Yeah, not that one.
Okay, then yes.
This is it, right?
Mhm.
Okay, so you took the derivative of this and you got this right here.
No, I got 3x squared and then sine x plus 3x squared cosine x.
Oh, okay. So you took the derivative of the x cubed twice. So this is a product, right? This x cubed sine x. So you first start by taking the derivative of this one. Let me just write it down.
Okay.
So we have this right here is x cubed times sine x. So we can treat this product as like this is the f and this is the g. And so we just need the formula f prime times g plus g prime times f. So what is f prime?
F prime is 3x to the second power.
Okay, times g, which is
sine x.
okay, then plus g prime. What's the derivative of g?
It's cosine x.
Okay, and then times f. What's f?
X to the third.
X to the third. You put 3x squared, right? That's what you. That's what you had said, right? So that right there is just the derivative of the top, right? Which goes right here.
Okay.
I still feel like you're missing something here.
No, I understand it. It's just that so okay, so you get that from the product rule, right? And then when the formula for the quotient rule, aren't you supposed to find the derivative again?
No.
From that? Does that make sense?
Okay, yeah, yes, that's, so think about it this way. I think I have another way you can look at this maybe. Let's say that you have y equals just something divided by something else, a rectangle and a circle, okay?
Okay.
To make things simple. If you want to know the derivative of this, what you're going to do is you're going to take the derivative of the rectangle, you're going to multiply times the circle, then you're going to take derivative of the circle and multiply it times the rectangle, and then divide the whole thing by the circle square. Does that kind of make sense, what I'm saying?
Yes.
This is the same thing as if I said if you have f over g and you take the derivative, you do f prime times g minus g prime times f all over g squared. That's the same thing, except instead of using f and g, I'm just using symbols. Are you okay with that?
Okay. Yes.
Now, when you do this step right here, right, this step in yellow, you have to take derivative of whatever the top was and put it right here. So when you looked at that up here, it was x cubed sine x. When you looked at this, you say, oh, wait a minute, hold on, I have a product right here. So when I go to take the derivative of this, I have to use the product rule, which is like a separate problem. And you do that, you get 3x squared sine x plus, cosine x times x cubed. But that is the derivative of the top. So that gets slapped in right here. You don't have to take the derivative again. That is the derivative of the top.
Oh, okay.
Sure?
Okay. No, I get it. I just when I went through it the first time, I just like I know that like you're supposed to plug it in, but I guess I didn't like I knew that it was a derivative, but for the quotient rule, it's still asking for the derivative. So I just thought you had to do it again.
The only thing that has to go here is whatever the derivative of the top is. If the top is something simple, you just slap it here. But if it's something complicated, like a product rule, then you have to go figure out what that is and then slap that in here. But you're not going to take the derivative again. That is the derivative of the top.
Okay, that makes sense.
Okay.
Okay, thank you.
Professor, can I ask you a quick question about the quiz?
Yes.
For this for this problem, do I have to first find the derivative, right? Or no? Okay.
Yeah, because you need, in order to find the equation of the tangent line, you have to be able to complete the formula for the equation of the tangent line, which is this.
Yeah.
And that means you need to know what the slope is. And the slope is going to be the derivative of this function at the point we're talking about, which is at 1. So you need to know the derivative at 1. Is that okay?
Okay. Okay, yeah. Thank you. Professor, just to make sure, at the end, I will just have the slope, right? So I will not have like the y one value, I don't know how to call it, and the x, it will just be like this, the slope.
The m is going to be the slope,
Yeah,
which is the derivative. Then you need x1 and y1, right?
okay,
x1 is just 1.
okay. And the y will be when,
Well, no, the y won't be 1. The y is what you get when you plug 1 into the original function, because this point has to be on the original curve. So you have to figure out what you get when you plug 1 into the function, not the derivative.
okay,
The
okay,
deri-
okay,
Yeah, 1 plugged into the derivative gives you the slope of the tangent line. 1 plugged into the original function gives you the y value of the point.
okay, I see. Okay, thank you.
Okay. You're good to go, Christian.
Professor, can we go already?
Yeah, you're free to go.
Okay, thank you.
Everybody's free to go unless you have a question.
Oh, was there like any? Oh, go ahead.
Oh no, I'll ask in a second. It's fine.
Yeah, I was just gonna say, was there any homework due? I guess besides the quiz thing.
Yeah, so as far as the homework is concerned, you should pretty much try everything from 2.3 and 2.4. I mean, these homeworks are, we've done the basic differentiation formulas. We did the product and quotient rule. Now it's just a matter of practicing. Yeah. Yeah, so I would definitely, these we've covered, I would definitely work on preparing for the exam by, the review is one thing, but you should be comfortable with everything. So everything in blue there, you should try and work on over the weekend.
Okay.
Yeah. Yeah, y'all are free to go unless you have a question.
Is it right if I ask a question about the problem? Because I was, so I made it to the part I got through with all the stuff. So I added in the x because whatever I got for the problem, or for the difference quotient, I got 3x squared plus 1 squared, or like that whole problem squared, minus 6x times x cubed plus x all over 3x squared plus 1 squared. And then I plugged in the 1, and my at the end of that, you should have like 1/4, right? And that would be the that would be the slope, right?
Okay, yeah.
Or that would be the y.
So you're asking me, you took the derivative and then you plugged 1 into it and you got 1/4.
Yes.
Okay, and then you're asking me, is that the slope of the tangent line?
Yes, because well, no, wait, because you put the x in there, that would be the y, right?
No, if you're plugging the x into the derivative, that gives you the slope of the tangent line.
Okay. Oh, you would plug in the x to the original one.
Yes, to get the y.
Okay, yeah, and then so the 1/4 is the slope.
Yep.
Then awesome. Okay, thank you.
Yep.
So another quick question. As far as this whole question, you could use what we learned today about the quotient, right? Because that's instead of using the limit thing that we
yeah. No, you wouldn't be able to do it with the limit. It would be too hard. Yeah. You want to use the quotient rule.
Okay. Because that's the same thing as finding like the dirt. Okay.
Yep. Yep. Yeah, so now what we're doing is we're actually utilizing what we learned today, that we can now find the derivative of a function. And then if you know what value you're talking about, like here x is 1, then you can tell me the slope of the tangent line there. But that would just give you the slope. You have to find the equation. So you need to just go back and look at your previous notes when we were finding equations of tangent lines. We used a certain formula for it from college algebra.
The y minus y1 equals m in parentheses. That one?
Yeah, you're going to use that. Y minus y1 equals m times x minus x1. The m you're going to get from taking the derivative of the function and plugging 1 into it. The x1, well, that's 1. That comes from here. And the y1, that's kind of the question that Brian was asking. It's like, where do you get the y coordinate? But this tangent line must touch the original curve, which means it must come off of this function. Must be on that function. So all you're going to do here is plug 1 into the original function, not to the derivative, but into the original function to get your y value.
So you take the derivative of f of x, right? And then you plug in 1 once you get that derivative. That's what you mean by the derivative of 1 right here, where m is.
Yeah, let me do this. Let me go back back to this. Let's see, limits. Okay, last class we were talking about how if you're trying to find the slope of the tangent line to a function at a point, right? The slope of the tangent line.
Yeah.
Is you take the derivative, you find the derivative, right? Find the derivative at that value 3. And that'll give you the slope. If you want the equation of the tangent line, then at a certain value, then you use this formula. The m is the derivative at 3. The x1 is the 3, and the y1 is what you get when you plug 3 into the original function. It's the y coordinate on the graph. Maybe I can illustrate it this way. Let me x cubed plus x. Here's the graph that we're looking at. And we want to know the slope of the tangent line at x equals 1. So that means you have to go and plug 1 into the function and figure out what is this point right here. So what's the x coordinate and y coordinate? Well, you know the x coordinate is 1, but the y coordinate lives on this graph. So you just have to take 1 and plug it into that, and that'll give you your y coordinate. That'll give you the point on the line. Then you need the actual slope of the tangent line, and that you get by plugging 1 into the derivative, and that'll give you a number, and that will be your slope.
Okay. Gotcha. Thank you.
Oh, so when you plug in 1 and then when you get the value, that's basically the y, is what it's giving you.
When you're plugging 1 into what?
The equation.
The original function. Yes.
Yes.
That'll give you the
Okay.
1.
Okay. I was making sure about that.
But when you plug 1 into the derivative, that gives you the slope of the tangent line.
Okay.